Back to another video, guys. You're on Physics with Daniel Dallas. We continue doing the topic dedicated to thermal physics, and right now we on subsection for gas state equations for ideal gas, and it's all about microscopic parameters like pressure, volume, temperature, and number of moles. So make sure you understand how the gas equation looks like, what conditions are applicable to the gas in order to consider this gas as the ideal gas. And today I want to give you another problem. So problem 2 is basically describes the whole set of problems dedicated to gas leakage. So in that case, we're gonna go to one interesting problem where we have two tanks connected with the tube right there, and we have a valve, basically a faucet, that can be opened under certain conditions. So obviously, as you understand how valve works, it works in this way so that if the pressure, let's say in tank 1, exceeds the pressure in tank 2 by a certain amount that actually valve designed for, you have gas leakage. All right, it's all about transfer gas from one vessel into another one, and that's why I describe, and this problem describe the whole class of problems dedicated to it. So finally, you need to find probably the pressure that range up to certain conditions when you have when the portion of gas has been transferred from one tank into another one. And also it's all about, you need to find probably the mass of gas transferred. So it might be different parameters in a certain problem. But here we have a look at finding pressure P1 and P2 after certain conditions. Alright, so read this problem carefully, pause the video, try to do around, and here's going to be my explanation soon. Alright, so I'm just going to squeeze a little bit so that we have full picture of what's happening here. And we're going to start. So we're going to start, as normally the starting point here is to consider states that you have before the process has been taken or takes place, and after that. So, and before the leakage of the gas, we have state 0 that can be described by the following parameters. So basically all portion of gas we have in the tank 1. So by the way, both tanks are identical, so that means they're made of the same material with the same volumes. So I marked both volumes as V, and that's very significant for us. And we have the whole gas contained in tank 1. So pressure and temperature. So pressure is P0, 10 to the power 5, basically 1 atmosphere. Pascals, 10 to the power 5 pascals, and temperature 0, which is 20 degrees. All right, so we have some quantity of quantity of gas, so that's why we can mark as probably, let's say, nu 1 or nu 0. So that's my, let's put nu 1. All right, that's gonna be the quantity of gas here. All right, so let's set up the equation P0 for the state 0. So the equation will look like P0 times V, volume, is going to be equal to nu 1, the initial portion of gas, times T0. That's the initial conditions. All right. After the process of leakage has took the place, what you can see here, of course, when you heat it up, so after heating up, so here is the fire burner, doesn't matter. So you heat it up, heating. Obviously temperature and the tank 1 is rising, pressure is rising, and that means the new pressure becomes definitely higher than 10 to the power 5. So let's say that we have a pressure exceeding this value 1.2 to the times to the 10 to the power 5. That means that valve is in the open state, and that means a portion of gas should leak into tank 2 and fill it up, because right now, so in state 0, there were no gas at all. There was vacuum, right? Okay, so that means we have until the pressure in both tanks become P2 and P1, so that the difference, sorry, the way back, set up P1 because that's tank 1 and P2, until, so the leakage of gas will be until their difference in pressures, obviously because the initial pressure in tank 1 was 10 to the power 5 and in tank 2 there was basically 0, there is no pressure at all, so we have P1 definitely more than P2, so that means the difference in those pressure will not exceed your certain value, 1.2 to the power 10 times 10 to the power 5. So that means we can state that delta P, we mark this delta P, okay, delta P 1.2 to times 10 to the power 5 pascals, all right, and that means the leakage will be stopped at certain conditions when the difference in pressure will be strictly equal to change in pressure, right? So that's certain, let's say, barrier. Okay. So from there, we have also new temperature, which is, let's say, T2 here, and new number of moles in each tank. So let it be new 1 and new 2. All right. So that means it's better to consider the initial quantity is going to be new 0 and new 0 here. All right, it's better for our consideration. All right, so we have all parameters, volumes stay the same, so that's why we can write state of this, the equation of the state of the gas. So that means we can write P1V is going to be new 1R and T2, new temperature, all right? And for the second tank, it's going to be P2V, another quantity, new 2, RT2, the same temperature, but the final one. So T2 is the same temperature because they are identical, and basically the gas, so after this tank has been heated up, the gas with T2 leaked into tank 2, and we assume that there is no energy loss, so temperature stays the same, but the gas now, the portion of gas is in the tank 2. All right, so what we're going to do, we can express, so make the difference, or just simply express. So let me see what we can do. We can simply express P2, we just continue writing and say, okay, the whole portion of gas in tank 1 and tank 2 together, when you add it up, will give you the initial quantity. So number of moles that you have originally, so new 0. It means that new 1 plus new 2. So that means we can express new 2 from here and write as new 0 minus new 1 times RT2. Okay, that's what we'll have right now. And of course, new 0 and new 1 can be expressed from those equations. So that means we can express them from equation 1 and equation 2 and plug those values into equation 3. So let's have a look carefully. I'll just do it quick. So P2 times V, okay, P2 times V is going to be equal to new 0 is simply from here is going to be P0V over RT0. Next, we subtract, take away new 1, which is P1 V over RT2. Okay, and we multiply both by RT2. So finally, out of this consideration, we can state that P2, the final pressure, can be expressed through P2 can be expressed using this formula, can be expressed in the following way. So it's going to be P0 over T0 minus P1 over T2 and times T2. So right now we have this as the final expression, almost the final expression for P2. All right, but of course we need to add another conditions. Remember, we used to told that we have change in pressure right now, change in pressure not exceeding this limited value 1.2 times 10 to the power 5. So the limited case is when they're equal to delta P. So that means we can express P2 through P1, all right? Because we have P1 here in the equation, so we can finally solve for P1, but first we need to express P2. So using this equation, we can express P2 from there. So P2 is simply P1 minus delta P. And we can plug in, all right? So what I'm going to do, I'm just going to plug here, right? So let me see and just go probably to another one. Okay, so I hope, yes, I hope we got everything that we want. All right, and right now what I'm going to do, I'm just going to rearrange our equation and try to express. So we don't need that. So we just need to express P2 and plug instead of P2 here. So that's why we can find P1 finally. So right now we have P1 minus delta P is going to be equal to, let's multiply out, and we get P0 over T0 times T2 and minus P1. So now combine P1 here and express P1. So P1 finally is going to be equal to P0 T2 over T0 and plus delta P and everything divided by 2 or times 1 over 2. So that's going to be the final expression for P1, because right now we are given all the values. Let's check. So we're given P0, we're given T0 and T2. So in our case, T2, they were heated up to 100 Celsius. So T0 initial temperature is going to be 20 degrees. Of course, you need to convert into kelvins and SI units, so we need to convert both in kelvins and just plug into. So our delta P is 1.2 times 10 to the power 5 pascals. Okay, and just right now let's calculate. So what I've calculated here, I found that P1, our final pressure in tank 1, so right here, is going to be 1.19 times 10 to the power 5. So it's going to be 1.19 times 10 to the power 5 pascals. All right, so that's the standard form that we're supposed to have. And finally we need to calculate P2, but P2 is simply P1 minus delta P, so we need to take away 1.2. So P2 is simply P1 minus delta P, and if we calculate, we'll get 0.086 times 10 to the power 5. But now we need to transfer decimal point here twice. So that means we've got 8.6 times 10 to the power 3 pascals. So that's going to be final pressure P2 in the second tank. It's going to be 8.6 times 10 to the power 3 pascals. All right, so that's the solution. So let's have a look at the complete steps. So that's the first one, where we express P2 And finally, we got the formula for P1 here, and also for P2. Sorry, let's simply rearrange it. All right, so hope you like that. This sort of medium, maybe hard level, because you need to understand what's happening here. It's not really hard, so that's why it's sort of medium hard level. But I think I clarify how to work with valves. What's the condition where it opens? According to the problem, it's opened when the difference in pressures in two tanks exceeds 1.2 10 to the power 5. So that means the leakage will stop at this time when pressure will have this difference. All right. Subscribe if you're new here and smash the like button if you like that. Hope I clarify truly. And that's definitely for advanced students, so it might be suitable also for A-level and IBHL physics, and also for JEE Mains. I think so. All right. See you next time.